In this lecture, we're going to move on with waves by talking about the fact that waves can travel. And I have a pretty cool contraption here. It's called a torsion wave apparatus. And so what's going on with this, put it up so you can see a little better, is that there's a wire going through the spine of this thing, and each one of these little pieces of rod is connected to that wire. So as the wire torques a little bit, it makes all of these pieces of all these steel rods bounce up and down. And it's pretty cool because I can actually excite a traveling wave by doing that. Okay, so to me, sort of the coolest thing about waves is that they are able to transfer energy over really long distances. They don't have to transfer any matter. And so here's what I mean by that. Right? If I give a little pulse on this side, right, I can set off a sequence of interactions that goes back and forth and back and forth. Okay? So this rod over here on the side, it hasn't traveled. It's not traveling back and forth. So there's not matter traveling. But somehow, just by giving a little pulse here, we're able to make a wave. We're able to transfer energy over long distances. So this is the idea of a traveling wave. Okay. A couple of things that I want to talk about with traveling waves before we're kind of done with this demo is that we have two different kinds of traveling waves that we can have. What I've just been showing you is a transverse wave. Okay. So this transverse wave is propagating because the direction of motion is along this apparatus, but the direction, so the energy is moving this way, but actually the particles are moving up and down. So the matter is moving in a direction that is perpendicular to the wave motion. And this is called a transverse wave. And I can actually set up a standing wave if I want to on this thing as well. There's a transverse wave. A longitudinal wave is a different kind of wave. Let's see if we can make it show up. So I want you to watch what happens to this line right here as I send a pulse back and down. So now instead of starting the wave by making this go up and down, I'm going to start the wave by making this go side to side. It's a little bit less obvious. But did you see the first pulse of energy? It's sort of going back and forth like that. So this is called a longitudinal wave. I also like to call this a compression wave because that's the more physically intuitive name for it to me. So what's happening is that in sort of sticking together a bunch of particles, if I let them go, they can send energy apart. So now the energy is still moving left, right here, but the particles are also moving left, right, just like that. Those two different kinds of waves. Transverse waves, like that, and longitudinal waves, like that. Okay, I think that is probably good for starting with this. Yeah, so let's go do a little on the board stuff, or on the video stuff, I guess. Okay, so we previously talked about this. So these were types of waves, so transverse versus longitudinal waves. And so we've already kind of talked about this, so I'll go through this quickly. Right, here's what the transverse wave looks like. So the motion of the particles is up and down, whereas the motion of the energy is left to right. That's a transverse wave. Longitudinal or compression waves is that we make little spots of compressions and rarefactions, opposite of compression, as we move through here. Okay. Our next thing to talk about is just to define some letters. So we've already defined amplitude, but we'll define it again. So the amplitude of a wave, of course, the metric unit of any length would be meters, so we'll measure that in meters. The wavelength is this. So the wavelength is the distance for one complete oscillation. Okay, so if we want to start from here to here, that would be one wavelength. From crest to crest, that's one wavelength. From trough to trough, that's another wavelength. From this little spot here, which is sort of halfway between the crest, or between the zero and the trough, to this point here, those are all the same wavelength. And for the type of waves that we're going to be considering in this class, right, the wavelength is not something that will change. So if it's 1 meter here, then it's 1 meter here, it's 1 meter everywhere. Waves can also have, of course, frequency and motion. So that's like the amount of time, if this was a traveling wave. Right, as this wave propagates to the right, so if it was moving to the right, the amount of time it would take for a whole oscillation to pass through a single spot, which seems like it's the same thing as wavelength, but it's not. And we'll talk more about that as a pretty subtle concept. And we can talk about velocity of a wave, right? This right here, if this whole wave is propagating like it was with that demo that I just showed you, then we can think about the speed of a wave as being dependent on its wavelength and its frequency. And this looks like a whole new formula, but it's not, because we know that velocity is meters per second, right? So it's distance traveled over time, right? The distance that a wave travels in a single period. So let's think about a time period of a single period. So in a single period, the distance that it should travel should be one wavelength. And of course, I know that T is 1 over F, right? So I could plug this in and say that V is lambda times F. And basically, I have just derived this formula from the definition of velocity. This equation is also on the equation sheet, so you don't need to derive it for yourself. I just wanted you to see where it comes from. Just to prove to you where it is on your equation sheet. It's right here. Okay. Also, since I'm looking at it, these two equations right here, I don't think there won't be problems on your homework or on the test where you need to use those equations. So they come from your book. Your book does some things with them, but we won't go that far. All right. So as this wave moves, here's an example of a kind of wave. So a sound wave is a longitudinal or a compression wave. So what actually goes on in sound is that at the frequency of whatever sound wave it is that it's making, that drum head goes out and in and out and in and out and in. And when it punches out, like it is how it is right here, it squishes the air particles together. And then when it is in, it does the opposite of squishing those air particles together. And so over time, you can get, if you're going out and in and out and in and out and in really quickly, you can get this pattern of longitude or of compression waves that are traveling out that way. And I have a video that I wanted to show you about this that is super cool. We can hear sounds because our ears are tuned to be able to detect what frequencies are happening. But actually, 6 hertz, that's 6 cycles per second. We can't really see sound waves. They're too fast. So this guy has a subwoofer that he is using. And he is going to play a sound with his subwoofer at a set frequency of 6 hertz. So he pushes play. Now he's kind of making it bigger. And you can't hear it, so have fun trying to listen to it. But he has that connected up to a speaker. But do you see that the in and out motion? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It's at 6 hertz, and it's going in and out 6 times every second. So this is what all speakers do, but usually they go at a frequency much faster than 6 hertz so that we can't hear it. So what he's doing there, I'll pause it. what he was doing there at the end. I'll watch it and see if you can guess what he's doing. So he wasn't he wasn't changing the 1, 2, 3, 4, 5, 6. It was still going at 6 hertz, but he was making it louder and softer. And you could see that right when there was a big displacement, it would be in and out quite a bit. And when there was a small displacement, that's when the speaker was playing softly. Loud, soft, like that. Okay, so now he's going to play it at 3 hertz. So that will be 3 cycles per second. 1, 2, 3, 1, 2, 3, 1, 2, 3, just like that. There it is, going in and out at 1 cycle per second. So that's how speakers work, okay? So they create these compression waves that travel through the air, and they go from there. Don't need you. Let's do that. Okay. So earthquakes are another example of waves. I mean, waves are everywhere. So we'll just highlight a few of them. There's actually 2 different kinds of waves that are initiated when you have an earthquake. We have S waves and P waves. So S waves are these transverse waves that have the up and down motion. These waves are the destructive waves, right? If you are a house, going up and down is quite a bit more destructive than going side to side. But both of these waves are always initiated when you have an earthquake. But it turns out that these P waves are faster. So, not in a big way, but in a few seconds, right? You can know that an earthquake is coming by detecting the motion of the ground through a P wave. So I guess if you detect the P wave, that gives you, enough time to get to the frame of a door before the big one comes. And if you live in earthquake-prone areas, or you have ever lived in earthquake-prone areas, you might have been told things like this, right? Like it's always, like you always have, from when you first feel it, you always have just a little bit of time, enough time to get to a safe spot. And that's why, because the P wave hits you first. Okay, so how fast do waves move? So the wave speed, so how fast does it move back and forth, does not depend on the size and shape of the pulse. This is the next version of amplitude doesn't matter. So another theme in these chapters of waves is like the shape of the pulse. It can be a sine wave that looks like this. It could be some sort of really weird wave that looked like this. It could be a wave that's shaped like a funny person with a happy face. If it's moving like this, the size and the shape of the wave doesn't influence how fast it travels. The only thing that influences how fast it travels are the tension and the thickness of the string. So we'll call mu. This is the linear mass density. So what does that even mean? The linear mass density is mass, which we measure in kilograms, and length of the string, which we measure in meters. And I'd love to show you this, but unfortunately, it just doesn't seem like the tools that I have are making it be very visible on the webcam. On the next video, I'll get out some stringed instruments and we can play around with that, but not right at this time. So the speed of the wave depends on how tight the string is, and this thing here, which we're calling the linear mass density, but let's just think of this as being how heavy it is per unit how long it is, okay? So a really thick, heavy string will have a large linear mass density, and a really thin, light string will have a really small linear mass density. Okay, so let's do an example about spiders. So spiders, the way that they detect their lunch is that they are very sensitive to these vibrations. So they spin this web, and they sit at the center of the web with one leg on each strand, right, so that they can feel when something lands on it. By knowing which strand vibrated the most, they can know what direction they need to travel to get to it. So they monitor the radial threads for vibration when an insect lands. So these threads are made out of a silk that has a linear mass density of that. So that will be that mu. And it has a tension of 0.4 newtons. And these are both typical numbers. And we want an insect to land 30 centimeters away from the spider. And we want to know how long does it take that pulse? How long did it take before the spider feels that traveling wave that's generated by that land? So we just had the formula for this up on the previous slide. So I'll go ahead and write down that it's the tension divided by the linear mass density. Transverse waves on a chord are right here, so they're the bottom right-hand corner of this piece of your equation sheet. And so everything here is very nicely in, so I'll write down what we know. So this one here is mu. This one here is the tension, so we'll call that F sub t. And this here is the distance. Okay, so I can very easily calculate the speed of these waves. So let's calculate the speed of these waves, and we'll see where we are from there. So this is 0.40 newtons divided by 1.0 times 10 to the negative fifth kilograms per meter. And let's do the square root of 0.4 divided by 1. I don't like this calculator. I'm going to do it in 1 times 10 to the negative fifth. See if that gives me the right answer. It did. I must have learned how to use this calculator more than I used to. So that is 200 meters per second. Okay, so that's how fast the waves will travel on this string. And that's not how long, what we're looking for though. We are looking for how long will it take for the spider to find out. So we know the speed, we know the distance, and we want the time. That sounds like the definition of velocity to me. So I'm going to write that the definition of velocity is distance over time. Okay, so I'm solving for time, so it's in the bottom. So let me think about this as being a cross-multiplying problem. So I'll cross-multiply. I'll put v over 1, so I have something to multiply with distance. So this will be time times velocity equals distance times 1, but I'm going to ignore the distance. And now I can divide both sides by v, so that the v cancels, and I get that time is distance over velocity. And now I'm ready to plug in my numbers. The distance is 30 centimeters. I want to make sure I convert that into metric. So that was 0.30 meters divided by 200 meters per second. And even my crummy calculator can do that one easily. Is 1.5 times 10 to the negative third seconds. Pretty fast. There we go. A little over a millisecond before it travels. Let's think about sig figs and make sure that we are doing everything okay with sig figs. This one has 2, this one has 2. As this one is written, it only has 1. I'm going to go ahead and retroactively adjust the problem so that I don't have to, so that I can give it 2 sig figs so that I can round that to 1. Okay. Okay. So let's talk about how we draw these on a piece of paper. I have a piece of paper somewhere over here. Okay. All right. So I want to draw my wave. And this is something that you should get out a piece of paper and plan on sort of taking a piece of paper to write this out. Okay. So we're going to draw this on a piece of paper, which is snapshot versus history graph. Okay, so if you're drawing what's called a snapshot graph, that's your way of drawing what looks like if you took a camera and took a photograph of the wave at one point in time. Okay, so a snapshot graph is a graph that looks like this. Right, X is on the x-axis and Y is on the y-axis, and we can think about sort of what the wave looks like as being something like that. Okay, and now if I want to visualize that my wave is moving, I have to put a little thing here to say that my wave is moving to the right. But we kind of have three dimensions here, right? We have X and Y for what the wave looks like at a snapshot in a period of time. And then this third dimension, which is V. So another way to visualize this graph would be, instead of drawing a snapshot graph, we could draw a history graph. And so a history graph is a little less intuitive, but we're going to have Y and T. So for our history graph, this is the history of a single spot in the rope. Okay, so if this is my little chunk, there's a little chunk of rope right here. As this wave propagates to the right, a short time later, my wave is going to look like this. Looks like it didn't show up very well on the screen, so I'll draw this in green just to make sure you can see it on the video. Okay, so as this wave shifts over to the right, a little bit later, the wave has moved to the right. Okay, so if you're a chunk of matter on this string, you haven't moved to the right, right? You're stuck right here, you're on the string. But now what you have done is moved up. Does that make sense? Okay, so a snapshot graph is like taking a photograph of the graph. A history graph is like drawing out the motion of this chunk of string as it goes up and down as this wave passes through. So I'm going to draw a few snapshot graphs history graphs of wave motion. So let's go with first, consider this non-symmetric wave. And it looks like this. So, sorry, I should make sure that I label my axes. So this is going to be a snapshot graph of it. So it's steep in the beginning, and it's shallow in the end, and it's moving to the right. Okay, so a short time later, it's going to look like this. It's not going to change its shape, but it is going to change where it is. So it looks like that. And a little while after that, it's going to be, I'll do dashed lines for my third time. And last but not least, I guess I'm running out of colors, so I'm gonna just do kind of squiggly lines for the last one. So there's my snapshot. At 4 times. And this is t equals 1, here's t equals 2, t equals 3, and t equals 4. Okay, so let's go ahead and look at the motion of a particle that is right, where do I want to put it? Well, let's just put it here. I realize that I have done backwards from what I intended to do, so it's going to be a little bit different than that PowerPoint is, but that's just fine. Okay, so maybe let's think about, I want it to be, thinking in real time. It's so hard. Let's put it here. Okay, so let's think about the motion of a particle. Here. Okay, so what is going to go on with this thing is that, right, at the first time, that's right here, and then we go a short time later, we're up to the green line. So it's going up, kind of like this. Okay, so it went a pretty short distance. It went up a short distance. At the second time, it's sort of, now we're on to this one. So it's going to move and it's going to go here. And then as the next time goes through, instead of being up here, it's going to go down. So unsurprisingly, I haven't chosen the most illustrative time since I was kind of thinking on my feet. But the thing to do here, can I zoom this in? Let me try and make it bigger. If it will let me do that. The thing that I want to point out here is that, right, this first time, when this less steep part of the wave was coming through us, we only went up a little bit. We only had to go up a little bit to get from the pencil line up to the green line. But then when we were on the back side of the wave, when this steeper part was passing through us, we went down a lot. Okay, so let's try to see what that looks like on a history graph. So we're going to go talk about this little piece of particle. So if we're here, we'll start here where we're undisplaced. So here we'll have y and t. We start out undisplaced and we move up just a little bit, up just a little bit, and then up just a little bit. Okay, so, and this continues sort of until the wave gets here. Does that make sense? So we're going to keep going up just a little bit, the same amount, every little chunk of time, every second, until eventually we get up to here. So we're going to go up really slowly, like that. Okay, so we'll sort of we'll move up just a little bit. Oops, I didn't need to get all that in. We'll move up just a little bit. So here's 1, here's 2, we'll move up just a little bit. 3, move up just a little bit. For each chunk of time, we're moving up the same amount. Okay, now we're here. Okay, now let's make the wave move just a little bit farther. So the wave keeps going, but we're still on this little chunk of string. And now it's been going up this little chunk, and now it's going down even faster. Does that make sense? So when the shallow part of the wave was coming through us, we were only going up a little bit. But now that the steeper part of the wave is going past this little chunk of string, we start going down more. So let's call this 5 and 6, and now we're on to 7. So 5 and 6, we were just going up a little bit, and now between 6 and 7, we have to go down a lot. Between 7 and 8, we're going to go down a lot again, and then we'll land somewhere like that. And the reason that I've taken the time to go through this is to show you that, do you see how these things don't look the same? Right? Our snapshot graph was steep and then shallow. Our history graph is shallow and then steep. So they're just kind of different ways of visualizing what's going on. So here we're drawing that this little chunk of string goes up slowly and then it goes down quickly as the wave passes through. Okay, so, and I warned that this is going to look different than what was on the screen. And here's the proof. I drew my thing backwards. Nope, wrong direction. Should never try to figure out technology on the fly, but I just did, so we'll see. It seems like it worked okay. All right, so we moved as the wave moved, right, our snapshot graph. To get to the other snapshot graph, we sort of moved just a chunk of time, so it's moving a little bit. But if we try to turn our snapshot graphs into history graphs, we can think about this little particle moving in a way that is the mirror image of, they're mirror images of each other. Okay. Oh, and a fun fact about this, which makes things a little bit easier, is that if you're dealing with a symmetric wave like this, so this is not a symmetric wave, where it goes up quickly and then down slowly. But a symmetric wave, like a sine or a cosine is a symmetric wave, goes up and down the same. So the snapshot and history graphs represent different physics, but they do look the same. So that can make visualizing it a little bit easier. But I wanted to go through this slowly just so that we could start to get this feeling of these two different ways of thinking about the waves. All right. So pause it and do those two problems. And when you think you know, unpause it and we'll come check in. So here's the answer to 11.3. So we have a sinusoidal wave on the string as follows. We want to figure out the speed of the wave. So we have this formula for the speed of a wave. Well, I guess we've put up two formulas for the speed of the wave so far in this video. So I'll put up this one and also this one. This is not a very useful equation to me for this problem, so I'm going to go ahead and get rid of it. I have no idea what the tension of the spring is in the string is or what the density of the string looks like. So, but this one I do know quite a bit about. And I don't want you to be too, this version of the formula is the version that appears on your equation sheet, but I want you to be good at transferring this to something that would also have period. And the reason that it's nice to have period is because I can very easily read period off of this, okay? So one of these over here, this is going to let us tell wavelength very well. We can tell the wavelength of the wave here. It's the distance for one complete oscillation. So let's go crest to crest. We go from 0 to 0.6 meters. And here I can say that the period of the wave is 0.6 meters. So I plug in 0.6 meters here at wavelength. From this, I'm able very easily to tell what the period of the wave is. So I go crest to crest. I go from 0 to 0.2 seconds. So that is 0.2 seconds. Right? If I want to go from trough to trough, I go from 0.3 seconds to 0.5 seconds. That's the same period. I'll still get 0.2 seconds. This period is not frequency. So we can either change the formula, or we can just convert this to a frequency right away. Most people find it easier to convert this to a frequency right away. So I know that frequency is 1 over period. So 1 over 0.2, which is 5 inverse seconds, or 5 hertz. Okay, so now I'm ready to just plug these numbers in. So I have V is 0.6 meters times F, which is 5 inverse seconds, and that is 5 times 0.6. There we go. Next one, what's the frequency? So the frequency of this wave was 100 hertz. So we were able to figure out, well, we were told what the velocity is. So we have this same V is lambda F. So V is the wavelength times the frequency. And so I know 200 equals lambda, which will be the wavelength of the wave. And one complete cycle goes from 0 to 2, which is 2 meters, times F. Or it goes from 1 to 3, which is still 2 meters. Or it goes from 2.5 to 4.5, which is still 2 meters. So now I'll solve for F by dividing both sides by 2 and get that F is 100 hertz. 100 hertz is something, unlike 6 hertz, which I showed you on the speaker, something that you can actually hear. Here's what it sounds like. It's a very lovely note. It's a very low note. The limit of human hearing is 20, 10, 30, something like that hertz. It varies from individual to individual, and it depends somewhat on how many rock concerts you have attended in your life. Because as you listen to loud noises, your mom might have been wrong about the microwave, and that is going to hurt you, but your mom was right about going and attending loud things. They do ruin your ears. But what tends to happen is that your ability to hear things at high and low notes falls away. Okay, next we're going to talk about damped harmonic motion. So most motion is not simple harmonic motion, right? It's not this kind of motion where it goes up and down forever and it never stops. And actually this is not simple harmonic motion, because as you can see, what is happening to this is that it is slowing down slowly as it goes and loses some motion. So most motion is not simple harmonic motion, but damped harmonic motion. So let's talk about this. So I have a pretty cool video that I wanted to show, which is this one right here. So let's see what it looks like. So there's a pivot and a ruler, and underneath the ruler is a magnet and an aluminum block. So this is a perfect thing to show this chapter after we just finished talking about induction, because what is going to go on with this is another example of an eddy current or a braking force. So as that magnet moves, that will be a changing magnetic field. Well, if we have a changing magnetic field, that will induce a current in the aluminum block that's just behind it. And just like when I dropped that magnet through the aluminum tube, it slowed down. But anytime we have an induced current, there's going to be some sort of a braking force. So this magnet, as it moves back and forth, is actually going to experience a braking force that's going to cause it to slow down. Okay, and the closer the magnet gets to the aluminum block, the more this braking force is going to be influence its motion. So that's what we're going to watch. So this is pretty seriously underdamped oscillation. And as he moves that aluminum closer, there is now a changing magnetic field, because there's a magnet at the end of that wire that's inducing a current in that aluminum block. And there's a braking force that happens as a result of that. Just like in chapter 21 when I did that demo where I dropped the magnet through the pipe and it made the magnet take a long time to fall down. So the closer this aluminum gets, the closer we get to what's called critically damped, and we're getting pretty close to that right now. So this here I think is going to be the critically damped. And you can see that it never oscillated. It just went quickly to its equilibrium position. And now we are over damped, which is that it's still not going to oscillate, but it takes longer than it needs to get to its equilibrium position. So the dings are for the critically damped object. So there was our damped harmonic motion where we saw the underdamping when it went up and down a lot as it slowly lost its amplitude. Our critically damped when it never passed the equilibrium position, it just sort of went as quickly as possible down to unmoving. And overdamping when it took a really long time to get there. Okay, so there are times when we don't like damped harmonic motion, right? A clock or a watch. Right? If you have a grandfather clock, if you've ever had one, they don't plug into the wall. They just swing back and forth. But slowly over time, they go slow. They can lose their time. So what you need to do is every few weeks you get in there and you sort of wind it up. You kind of coil up a spring, to give it some extra potential energy, elastic potential energy, so that it can kind of keep it moving over time. There's also things where we do want damped harmonic motion. So this is the shocks in your car, right? So what we would like is to be the Lexus driver with our very fancy shocks, where we go over a bump and it sort of slowly puts us down into our seats. What we get is, the 1999 Toyota Corolla, where you go over a bump and you go over the bump and you go boing, 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 boing. That's because your spring has worn out and it is now underdamped instead of critically damped like it was trying to do in the first place. It's also how we design our buildings to be earthquake proof. So this photo is a photo of a building that's going up, and these are pistons here that are there for earthquake protection. So when the building goes up and down or side to side, as those S&P waves travel through it, they critically damp the building, so they'd be tuned so that they want to oscillate. They want to damp resonance they want to damp oscillations that happen that are on wavelengths and frequencies that are typical of an earthquake wave. So they prevent your building from going back and forth a lot. They just sort of like the shock absorbers. Okay, and I think we're going to keep going. So forced oscillations and resonance is our next topic. So almost every system in the world is damped. So if you want to keep it going, you got to force it, okay? And that's the idea of forced oscillations. Resonance is the idea that every oscillator in nature has frequencies that are natural to it to resonate. And we've already begun to talk about this principle when I talked about, right, this pendulum going back and forth, right? No matter what I do, this pendulum is going to go back and forth with this same frequency. The only way I can change that is if I change the length of the string. So if you've ever been to a playground, I feel like every kid has to learn this, right? Is that they need to learn the resonant frequency of the swing set, right? So how many times swing is going back and forth, and 2-year-old Johnny walks up and he's trying to push his sister, and he walks up and he gets there in the wrong spot. He tries to push at the wrong time and he just gets whacked. I have a really good video for this, but I went to, it's just a video of a bunch of playground kids getting knocked over. But I went to play it this morning, and YouTube told me that video had been made private, so I can't show it anymore. But still can kind of imagine what Johnny looks like when he goes to try to push his sister and he just gets whacked. So right, if you want this thing to oscillate, you need to not push it, not force it at any old oscillation. You need to force it at its resonant frequency, at a frequency that it wants to oscillate. Okay. Right, I have a recorder here, and when I do this, it plays a note. Yeah, it doesn't play any other note. If I don't kind of plug up any of these holes and change some things about the resonant frequency of this thing, it will only play that one note. And I can play it soft, I can play it loud, but it doesn't change the note. The only way that I can change the note is by plugging up these holes. And we'll talk in the next chapter about why these holes are spaced how they are. But I can go like this. Like that. Okay. So that is resonance with this. I also wanted to talk about how another resonant frequency example I have a fish tank filled with some water. And this is really a much better demo to do with the class. So try to imagine which sucker I got to come up to participate in this demo. If you have a person in your head, or it can just be me. I have a fish tank filled with some water, and it's green water so that you can see it. And as I walk across the room, not very much water in this, so I can walk across the room back and forth pretty easily, and it doesn't really affect much going on. But it turns out, and this is a good party trick for quarantine, if you hold it like this, the resonant frequency of the water as it sloshes back and forth, I can kind of make it slosh back and forth here. That's a wave. Yep, slosh back and forth wave. And it has a frequency that it likes to go at. You can kind of see my body wiggling back and forth. It matches the frequency of a person's typical gait. Okay, so if I walk with this in a way that is natural to me across the screen, I want you to watch what happens to the. You see them? The waves are getting pretty big, just because of me walking and holding this. If I filled this up anymore, then I would be getting splashed a lot more than I am right now. But I've already gotten a few splashes on me, so I'm going to quit. Okay, so this fish tank has a resonant frequency. It's a frequency that it wants to oscillate. Since we're here, we can talk about this thing having a resonant frequency. So this is more an idea of as this wave goes through here, it hits the end and then it starts to travel back. But if I can get multiple waves going at a time, I can induce resonance. Okay, and this oscillator is a complicated oscillator. It doesn't just have one resonant frequency. It has multiple, so I could get more resonance that way. Right? Let's see what else I can find. See if I can find the lowest resonant frequency. So why are we talking about resonant frequency? The point of resonant frequencies is a take-home point that I'd like you to come home with is that with resonance, a small amplitude forcing results in a large amplitude response. When an oscillator is forced at its resonant frequency. So if you want to think about the swing set analogy, right? So how does this end up being something that travels? If you want to have a big swing to your motion, you don't actually put a lot of force in it right away, right? You kind of force it at its resonant frequency, the right time in its motion every single time. And then eventually you get to this really large amplitude response. But you don't start with a large amplitude response, as long as you're pushing it at the right frequency. Every time you get a push, it will get bigger and bigger and bigger. But if you push it at the wrong time, then you just messed everything up, okay? So, right, you force it at a resonant frequency and there will be a large amplitude response. Uh-oh. Okay, so a couple more examples of resonance because it's a pretty fun topic. So a glass, if you hit it, right, you know it makes a ding. Right? That ding that it makes is its resonant frequency. So this is somebody can use that. You've heard this wives' tale of you can break a glass by singing at the right note. It turns out to be true.
Number 85 for the Voice Instructor Council. Yes!
So I'm going to play this again, and I want you to pay attention to what he does in the beginning, which is that he hits the glass a couple of times, and he's hearing that note. That is the note that corresponds to the resonant frequency of the glass. And then when he makes that same note really loudly, he can excite a resonant wave inside, a standing wave inside that glass. And as that wave is excited inside that glass, remember a small amplitude forcing has a large amplitude response with resonance. The wave actually makes the glass wiggle so much that it eventually cracks.
Number 85 for the Voice Instructor Council. Yes!
So I wanted to show is of the Millennium Bridge. So this was a bridge in London that opened. It was only open for 2 days before they had to shut it down for months to reinforce it. That video looked pretty cool though. And you can see actually what's going on here is, do you see the bridge is wiggling? So the engineers who designed this bridge didn't take into account the fact that the resonant frequency of this bridge, one of its resonant frequencies, matched the gait of people walking across the bridge. So they had built this whole bridge and they never had a giant group of people walking across it, so they had no idea that this would happen. They should really test for this, right? Engineers know to test for this, but they didn't. And actually, to this day, for reasons like this, military officers, when they walk across a bridge, will break that they all walk in rhythm. So they'll break that and walk in a more walk in a natural way, so that everybody's not taking a step at the exact same time. Because there was. All right, so let's go into the study area and find this video, and I'm going to show you how we get into this just so that you know where it is. So there's a lot of good videos in here. So I came from the main Pearson website and I clicked on access the study area, and then I come up here to the top and I'm going to change it to be chapter 11 because that's what we're looking for, and we'll click go. And there's 3 different PhET simulations that you can download. So these are kind of interesting ways that you can analyze different aspects of the chapter. What I would like to see is these vibrating rods videos. So that's what we're going to watch.
Here I have, in this demonstration, 4 sets of rods of different lengths, and they're all connected by this steel base. Now, the question is, if I pluck this large rod, how will the other rods respond? Will they all start to vibrate? Will the vibrations be different depending on the length, or will just the matching rod vibrate?
Okay, so if you have a guess, I will keep it going.
So as you can see, when I pluck this one, the matching rod starts to vibrate while the rest remain steady. This is because when I set this into oscillation and sent vibrations through the base of a certain frequency, the frequency of this rod, which was picked up by this rod since it has the same natural frequency as this one, and started to vibrate. The rest of these rods have different natural frequencies, which are not equal to the frequencies of these rods, and therefore they did not vibrate.
So what he said in the end is he said that these other rods here in the middle didn't match the natural frequency. Natural frequency is another word for resonant frequency. So what he's saying is that the resonant frequency of an oscillator, of a pendulum, depends on the length of the pendulum, and this is kind of a similar resonator to a pendulum. So it should make sense that the length of this cord here determines its resonant frequency. And since all of these rod lengths are different than that, the only one that will have a matching resonant frequency is the one that is the same there's a few examples of resonance, right? And again, small amplitude forcing results in a large amplitude response, and that oscillators will only oscillate at certain resonant frequencies. Okay. This is how your ears work. So inside your ear, you have an eardrum that vibrates in and out as those sound waves, those compression waves come through. So your eardrum vibrates, and that sets off a wave that travels into your cochlea and along the string. And this little line here actually has thousands of tiny little hairs, okay? And some of these hairs down here are pretty long hairs. Right, so some of these are longer hairs, and they're going to vibrate at a resonant frequency that is different than these waves, these hairs down here that have that are shorter. So right, the length of the string determines its resonant frequency, just like it does for any pendulum like that. And so when the sound comes in, a low frequency sound wave sort of resonates with, you know, these longer hairs down here. And that's connected to a neuron in your brain, and it knows that when this wiggles right here, that must mean that a low frequency sound wave has come in. And none of these other ones will wiggle when the low frequency sound wave comes in. Okay. And this is also unfortunately why when we get older, as we beat up on our ears, right, these little ones here, if we listen to something with lots of high frequency, large amplitude, so loud high notes, some of these basically just get blown out just like a speaker. So they stop working as well because, or they get damaged because they have been vibrated so much, like just like that glass just was that they broke. Okay. And that is as far as I was going to go in this video today.